Foundation Decentralized Trust meeting. And today's meeting, we're gonna focus on zero-knowledge proofs or SNARK programming, and we're gonna cover, or we'll do some brainstorming how zero-knowledge proofs or zero-knowledge programming or SNARK programming can be used for Hyperledger Fabric. We're gonna see a couple of examples as well, but there will be some general brainstorming as well. Perhaps just a few words on myself. Well, actually, I'm not a hardcore cryptographer. I'm rather a software engineer, and then I would say zero-knowledge programming or SNARK and STARK and similar designs are getting to be interesting for software developers as well, not just for hardcore mathematicians. And the reason is for that because there are many new platforms, development environment with which practically you can just program things without knowing some of the deep math. I wouldn't say that you will manage absolutely without math, but basically you can do something on a programming or software development side as well. So basically, again, I'm rather a software engineer, so I'm gonna cover things from a more general perspective, like as a software engineer or as a software developer, and not as a hardcore cryptographer or not as a hardcore mathematician. The agenda for today is the following. So first, I will have a few slides generally on zero-knowledge proofs. Again, it's gonna be a mathematical introduction. So we not gonna cover like polynomials over finite fields. And then, this one is more like a brainstorming meetup, how we can use like zero-knowledge or SNARK programming stuffs in application development for Hyperledger Fabric. It's not very common to use these structures for Hyperledger Fabric. It's more like hype for Ethereum. But basically, for this reason, I thought it would be like an interesting point, just brainstorming on how these patterns, how these zero-knowledge programming structures can be used with Hyperledger Fabric. Then after this brief introduction, I'm gonna cover a few examples. The first two examples gonna be like real-world examples. It's like a private signer and confidential transaction. These really exist for Hyperledger Fabric, and I'm just gonna cover a couple of other examples, again, more like from an application slide that could be actually done with Hyperledger Fabric, and it makes sense as well. I'm not quite sure if there are examples, but despite it can be interesting. So we're gonna cover like Mixer, like off-chain transactions, ZK rollups. I have one slide on exchange, especially on like off-chain order book matching. We might as well consider some other use cases, and then perhaps it's more important, or the most important part of the presentation is basically at the end. Not the Q&A, but I think this zero-knowledge and SNARK programming topic is getting to be more and more popular. And again, so basically not just for hardcore mathematicians, but rather for like blockchain developers as well, like application developers, and for like coders as well. So for this reason, I thought it's just not the easiest way or not the best way just to have like one or two presentations on the topic. But what we're gonna cover this year is that we just want to roll out basically a learning group for zero-knowledge programming, and then that's gonna be the announcement at the end. So I would encourage everybody just to stay till the end, because again, there will be like a learning group for zero-knowledge programming or zero-knowledge based application development. We're gonna cover like one session each month till the end of this year, and then I will cover some theoretical basics as well, but more like programming and application development. Again, each month there will be like one session. There will be like quizzes and basically like programming exercises as well. And then, well, if anybody manages to get till the end of the year, then you might expect some merge from Linux Foundation Decentralized Trust as well. So again, that's probably the last but one point is the hunting for the SNARK, which is like a zero-knowledge learning group in 2025. So basically, that's gonna be like the most important announcement. I would encourage again everybody just to stay till the end. So that's the agenda, and let me just start again just with two introductory sessions. One for like general zero knowledge proofs, and the other one just two slides for Hyperledger Fabric, in case you are not familiar with these topics. So the first is like zero knowledge proof. So basically, it's a proof of a statement. It's not absolutely a classical mathematical proof. I mean, it's a proof in a mathematical sense, but not absolutely like the, I mean, what you learned as a mathematical proof in an elementary school. Basically, it might be kind of a probabilistic proof as well. So it's not necessarily something which is 100% sure, and not necessarily something which is proved by a mathematical logic. And then what's important that if we speak of like zero knowledge proofs, then we usually consider two actors. And what is usual as in cryptography, these two actors are Alice and Bob. So if we speak of like a proof, basically, then we have these two actors, Alice and Bob. And basically the idea is that Alice tries to convince Bob for something. Alice tries to convince Bob that she knows something, and that's what we mean of proof. So again, it's not like a proof in mathematical logic, or not necessarily exactly the same. So the idea is again that we got Alice and we got Bob. These are two actors, and Alice wants to convince Bob that she knows something. She knows a statement, or she knows like kind of a secret information, and she tries to prove that for Bob, or convince Bob that she really knows this fact. She really knows something. So that's like a prover and verifier model. Alice is the prover here, and Bob is the verifier. Bob is practically the verifier here. And we can think of like zero knowledge proofs as well. Zero knowledge proof means that basically Alice tries to convince Bob that she knows a fact, and Bob gonna believe this fact. I mean, Bob gonna believe that Alice knows this fact, but in a way that Bob will not know exactly the fact itself. But despite he will be convinced that Alice knows some kind of a fact. Let me just give like a couple of examples. So one example is like a Sudoku. This is like a Sudoku puzzle here. Sudoku puzzle is like a couple of numbers, and then you just fill some of the numbers in a way that the sum of the rows and sum of the columns is, I don't know, equal or something. So that's like a puzzle. That's like a Sudoku puzzle. So let me imagine that the fact which for zero knowledge proof is the solution for the Sudoku puzzle, and in this way then Alice tries to convince Bob that she knows basically a solution for the Sudoku puzzle, in a way that Bob is fully convinced that Alice really knows the answer of this puzzle, but Bob itself will not know the result, the solution for this puzzle. That's like basically a zero knowledge proof. Another more mathematical example might be like the pre-image of a hash function. So Alice might try to convince Bob that she knows a pre-image of a hash function, in a way that Bob will be convinced that Alice really knows that she really knows the pre-image of a hash function, but Bob will not have this fact. So Bob will not know exactly what's the pre-image of this hash function. We can give like intuitive example for this one as well. Again, it's usually pretty mathematical, but the classical intuitive example is Waldo. If I can find Waldo. So the idea is that we get a picture full of people, and we have like Waldo or Wally. That's this guy. This guy is Waldo, or this guy is Wally. And then we can have the idea of having like a zero knowledge proof. There's a prover and the verifier, and the prover tries to convince the verifier. So like Alice tries to convince Bob that Waldo is somewhere on the picture, and Bob will be convinced that Waldo is really on the picture, but Bob will not know the exact location of Waldo or Wally. So that's the idea of a zero-knowledge proof. Again, this one is not mathematical, but we can try to imagine basically that we cover this somehow with like tricky solutions. So we can imagine like, I mean, let's have the idea, we just print out this piece of paper and then basically we give this piece of paper to Bob. Bob gonna create a lot of signatures on the other side of this picture. And then Alice will practically cut out the head of Waldo from this picture, and she will present the circle of this small circle with Waldo's head to Bob. And Bob can see basically that on the other side or on the same side, he has the signature basically. So he can be sure that basically the small circle with the head of Waldo was cut out from the original picture, but just based on this small circle, he will not know where was exactly Waldo located. So that's like one example. There can be like many other intuitive examples as well. It's perhaps important to note these are not mathematical examples. So usually if we consider like zero-knowledge proofs, we consider like more mathematical solutions. There's another thing as well. Again, these proofs can be probabilistics. So basically it might not 100% sure that like Waldo is on the picture. It might be like just kind of a probabilistic measure. So like 99% sure or 99.999% sure, but perhaps never 100% sure. That's one important characteristic. The other one is that such a proof might be interactive as well. So it might not work in a way that Alice shows something and Bob gonna be sure that it's okay, but there might be like a sequence of like messages, communications, and perhaps after this certain messages or certain protocol of messages, there can be like a probabilistic measure that a certain statement is true, or Alice knows a certain statement in a zero-knowledge sense. Certainly from an application perspective or from a blockchain perspective, zero-knowledge proofs that are non-interactive, so where we don't have these many messages like response and challenges, these are the most important ideas, or these are the most important solutions. It's just because if you have a zero-knowledge proof, usually you just write into blockchain and basically you just expect that everybody can validate it without like having many interactions. So just speaking of SNARK or ZK-SNARK, that's like one way of, or one idea of like zero-knowledge proofs. And then if we think of like SNARK or ZK-SNARK, what we usually mean is that we have a function. The function is kind of a computation, which is, I mean, practically just a box. And this box has like public and private inputs, and it is evaluated to true or false. Or if it is evaluated to a number, then I mean it can be just rearranged in a way that it is evaluated to true or false. And we got something which is a computation model here. That's pretty tricky, but I mean this computation model can be practically anything. If we need to program it, it depends on the development environment. So it might be like something crazy, which is like arithmetic circuit or rank 1 constraint. But anyway, this is just a general computation model. So we got here a computation, which is a function with some public input and private input. And what we're gonna do is that we just want to create a proof, basically, that this computation was evaluated to true. And this is what the prover does. And the verifier practically convinced like 99.999 that this function is really evaluated to true without knowing the private inputs. So this is the private input which is known only by Alice, and it will be not known by Bob practically. So if we speak of like SNARK, there are a couple of characteristics again, but this is like the computation model what we think of. And then this proof at the end must have a couple of like characteristics. So first, it should be like succinct. Succinct means it is a short proof. So basically, it's not a way that we just replace or somehow copy this full computation, and Bob just runs this full computation. So again, it must be a short proof. It must be a non-interactive proof. So usually, if we like speak of blockchain applications, we just don't expect much interactions. We want to create one proof that can be like written to the blockchain, and everybody just can validate it without interactions. We have some argument of knowledge. This is some information that the prover knows. This is usually the private input in this model practically. And then basically it can be zero knowledge. If zero knowledge, then the verifier, then Bob, will believe this proof practically in a way that he not knows practically. He doesn't know the private input. Private input is known only by Alice. So that's like SNARK and ZK-SNARKs. There are other ZK zero knowledge programming structures as well, but we not cover them at the moment. So just a slide on ZK programming again. So the math is pretty deep. We're just not gonna cover in details at the moment, but basically, if we consider things from more like a programmer or software developer point of view, what we basically have, we have like a couple of domain specific languages for this computation model. So for this business logic, I would say business logic. So we can implement our logic in like I wouldn't say necessarily high level language, but a higher level language. It's like Circum, Socrates, Noir, Kairos, and Zinc, and so on, Leo. These are like higher level languages. There's a compiler which compiles this to like a ZK friendly format. It's like rank 1 constraints or Planck style arithmetization or something crazy. And then basically there's a system which is the prover itself, which is like a full framework with which you can just create the proof, and then there's some support for the verifier as well, verifying this proof basically. So everything is basically given by the framework as well. That's from a more like from an engineer point of view. And again, there are like many structures. Basically, we usually say that cryptography is a zoo. So there are like many animals in the zoo. And then basically it's especially true for different zero knowledge and SNARK structures. So then we can compare like different SNARKs or even STARKs and other structures based on the size of the proof, the verification time. There's some idea about this setup, and then there's like one column or one attribute for post-quantum readiness. So in this sense, we can say like the easiest way or the most classical way is just use Groth 16, which is a small proof, which is a small verification time. The setup is a little bit tricky because there's like a special initialization setup which must be executed for each computation or for each different computation. So for each circuit, that's practically circuit is the computation model here, and then it is not post-quantum ready. And on the other side, there are like STARKs, which are actually not even SNARKs, but basically similar structures. They have like bigger size of proofs, bigger verification time, setup is better, and basically post-quantum readiness is better as well. And we have a couple of other solutions in between as well. Okay, so that's like a brief introduction to ZK from a more like from a programming perspective. And I have just 2 slides on Hyperledger Fabric in case you're not familiar with it. Basically, Hyperledger Fabric is like a consortium blockchain solution. So the idea is that things are not run by individual independent validators, for instance, in an anonymous way, but basically the whole system is run by companies practically. So we got one node which is run by one company and the second node by another one, and so on and so forth. Speaking of Hyperledger Fabric, usually there are like 2 general structures or architectures. One is more like a physical architecture, and the other one is a logical architecture. So if we speak of like physical architecture, we got like many different components which are specialized to doing one thing. So like peer making kind of a coordination for like running the smart contracts in a special way. Then chain code is the smart contract here. Then we got some state database, and we got like a different ordering service as well. Ordering service is responsible for putting like simulated transactions into blocks and so on and so forth. And what's perhaps more important, we have something which is a Fabric logical architecture. So the idea is again that this is run practically by organizations, by companies, and then we can have like several different setups. So like we get like here a 4 organizational setup, and then what's more important is that we can have like different channels. Channel is practically a physically separated blockchain. So in this setup, like we can have like one physically separated blockchain connecting like organization 1, organization 2, and organization 3. And then we can have a second channel as well, which connects only organization 2 and organization 4. And again, channels are practically physically separated blockchains. So basically we have here like 2 different blockchains in our setup. One connecting org1, org2, and org3, and another one is connecting like org2 and org4. And then, but there can be like many more as well. So we can imagine like other tricky solutions as well and setups. So having this introduction, let me just try to summarize and brainstorm on ideas how we can use like zero-knowledge protocols in Hyperledger Fabric. And the first one gonna be an existing solution. I call this pattern as a private signer. So the idea for Hyperledger Fabric is that, so I mean, for the idea is for most of the blockchains that we use something which is public-private keys, but it's more tricky in Fabric because what we have is like X509 certificates. So X509 certificate is practically the keys or the public keys with some meta information, and it can be signed like in a hierarchical sense with like different certificate authorities. So like X509 certificates, that's more like the, I would say, the enterprise version of public-private keys in a sense. And the problem is that if you sign a transaction, then some of the metadata of your signing key or signing X509 certificate will be visible practically on the blockchain. And if you think of like multi-organizational setup, it means if there's one signer from one organization and we got like a channel, then this signature can be seen practically for other organizations as well. So practically the information which is like in an X509 certificate will be visible for other organizations as well, which might not be the best idea. Which might not be the best case. So for this idea, we have something which is a private signer, and it's called identity mixer in Hyperledger Fabric. And it looks that way that basically for signing a transaction, not exactly an X509 certificate is used, but something which is a so-called verifiable credential. So verifiable credential is basically a piece of digital document with some signatures, but the idea for verifiable credential that there's like algorithms for that you can prove something with a verifiable credential in a way that not all of your information is revealed. So the best idea for a verifiable credential is like I don't know, it's like a driving license. So for instance, you want to just show to somebody your driving license in a way that it can be verified that that's a valid driving license, but no other information is revealed. So like not the date where you born or not the place where you born, even if that's on your driving license, it's just the information that's your driving license is valid. So that's like an idea for verifiable credential. And for verifiable credential, there's a way which is supported by zero-knowledge proofs to show part of, I mean, not show, but basically to demonstrate that part of the information on your verifiable credential is valid without showing these pieces of information. And that's, of course, done by zero-knowledge proofs. So basically, we got like identity mixer, and then you can create a signature of your transaction with this identity mixer signatures, basically in a way that some of your attributes, basically like name, like enrollment ID, and some other things are not revealed, basically, but some other information is revealed, like the organization unit or the role. So this like identity mixer, it's already in Fabric 1.4 as well, if I'm not mistaken. Usually it's just not very much used for some reason, but I would say it's like an interesting extension, and it's basically certainly used for using like zero-knowledge proofs with Hyperledger Fabric. Again, I just use this sample as a private signer, basically, and it basically hides the identity of the signer, but basically in a verifiable way. So in a cryptographically verifiable way. So basically, I can be sure that I have cryptographically the access and the necessary role as well for executing a certain transaction, but without revealing my exact identity. So that's one idea. The second pattern, I call it as a confidential transaction, and it's basically a pattern which can be found in like usually privacy coins. The trick is that basically it's based on a UTXO ledger. In case you're not familiar with a UTXO ledger, Hyperledger Fabric is not a UTXO ledger, but there's like extension for having a UTXO ledger. So basically, Bitcoin is a UTXO-based ledger. It's called the unspent transaction output-based ledger. Basically, what we have is coins. So we can have like coins. So this is like coin 1, this is like coin 2, and then we can have a transaction, and basically transactions. So this is like coin 1, coin 2. Transaction spends practically a few coins, and there will be like new coins created. So this is like C4. There might be like a C4 coins as well. Then these are basically the coins that are spent, and these are the coins that are not spent, and this is the transaction. So it's like a little bit like crazy. You can have like a second transaction, and then second transaction spends basically C3 and C4 and creates a new coin, which is like C5, and so on and so forth. And these coins will be spent, and C5 will not be spent. Again, it's originated from Bitcoin, but there's usage like for general purpose blockchain systems as well. So like R3 Corda is like rather a general purpose contracting system. So it manages like contracts practically, and instead of coins there are like contracts here, not smart contracts, but there might be like digitized contracts, and it uses exactly the same pattern. It uses exactly like unspent transaction based output system. And again, Fabric is in principle not a UTXO based system, but there are like UTXO extensions as well. So if you just take a look on GitHub, if I can open it, basically even in Fabric samples you find like UTXO based extensions as well for Hyperledger Fabric. It's not general purpose, so it's not like for general contract or contract management. It's rather for building up something which is a token based solution. And then if it's like a token based solution, then basically what we think of here like C1, C2, C3, and C4 and C5, these are not necessarily like bitcoins or coins, but kind of a special token, I would say. Okay. And again, there's like initiatives for UTXO ledgers, having like zero-knowledge proof based systems, where the idea is that transactions should be somehow kept confidential. I got a couple of like pictures here, if I can zoom in. So the idea general, so the problem is actually a bit like public ledgers is that even if like there's kind of a pseudonymization, so this is like not not necessarily a real word name of a person, but this is like a pseudonym of a person. So even if there's like kind of pseudonymization, there might be problem with this pseudonymization. So it might not necessarily be the best idea just to have like pseudonym identifiers on the blockchain. There might be a good idea to have something more which is more privacy, more confidential transactions. And the idea is here that we got a UTXO-based ledger, so this is like Bitcoin here, but again it's pretty similar like with like a Fabric-based UTXO ledger as well. And what we do, we're gonna hide the amounts, for instance, that we transact. So we will see here like the identities are pseudonymized, but we see here the exact amount that are transacted. So it might not be the best idea from a privacy perspective. We can have some improved privacy here. So what we can do is that we can hide these amounts basically on the blockchain. And the way we do it is that instead of having like amounts on the blockchain, so like free Bitcoins here, what we do is that we just commit somehow these, we just create a hash commitment, for instance, or a cryptographic commitment for these amounts. So for instance, instead of having free Bitcoin on the blockchain, we say that we just hash this free Bitcoin probably with a random number as well. So instead of free Bitcoin, what we have on the ledger is something which looks that way, which is practically a cryptographic commitment of the amount of Bitcoin or of the amount of token that is transacted. And of course, the major question is, okay, I mean that looks good, but so the point is, if you have like cryptographic commitments instead of Bitcoin or token amounts, then how can we basically make sure that the transaction is valid? How can like independent validators or more or less independent validators validate this transaction? And the idea is that for the correctness of these committed numbers, of this committed amount of tokens, we're just gonna give practically a zero-knowledge proof. And the zero-knowledge proof looks that way. So basically, again, the idea is that we hide something which is the amount of tokens that is transacted. So instead of amounts, we just use cryptographic commitments for the hash commitments, like hash commitments that might contain just the amount and the random number which is hashed. And for the verification or for the transaction as well, we just give like a zero-knowledge proof as well. That proves basically the correctness of the transaction, and it usually has like two things. One is like the correctness of the commitment, and the other one is the sum of the amounts. So I mean, if you just sum these two amounts, then we get practically if we just sum the inputs, we got the sum of the outputs minus some kind of a transaction fee if that exists basically. So that's what we have as a zero-knowledge proof. Plus, we will have the transaction with the signatures as well. And then if we have like a transaction with the correct signatures, plus the ZK commitments for the correctness of commitments and the sum of the amounts, then basically we can have like a valid transaction in a way that instead of like token amounts, we have like cryptographic commitments, and that can be validated practically by individual validators without knowing the exact amounts as well. So that's like the idea, and there's like a research paper, and then I think there was like an initial implementation for that as well. It's called like FabZK, which use like UTXO-based ledger with a similar idea. You can do this kind of a zero-knowledge proof with like a general SNARK system as well, but basically for efficiency reasons, there was like a dedicated zero-knowledge proof for that, which was realized by brothers and commitments. It was like more efficient, of course. Like efficiency is always a big question here. But anyway, it was FabZK. I'm not quite sure if the project really exists at the moment, but that was like a great idea. Like I don't know, 4 years ago. So the next idea or the next pattern is which is a mixer, and I mean, the ideas for mixer is that like having like one kind of a shielded pool, which like somehow hides basically originators and senders of a certain fund. And you might as well say it's, yeah, I mean, at the moment it's pretty controversial on public chains. I mean, the most famous or least famous example is Tornado Cash, which is like heavily discussed by different regulators, I would say. So it might not be fully legal on a public blockchain. But despite, I mean, if you think of like consortium blockchains, and I already mentioned Hyperledger Fabric is more like transacting between different organizations. So we might as well say, hey, we have like regulated organizations, regulated companies here anyway. So if we just think of that, these companies are regulated, they can do like KYCs basically somehow at the interface of the organization. So even if they are connected with a channel, and even if there's like a mixer in the middle of the blockchain, it might not be illegal at all, or it not be problematic at all. A mixer can ensure here that I mean these organizations will not fully see basically the originators or the recipients of the funds. But again, it can be a fully 100% legally compliant setup, as basically these are trusted organizations having like all the regulatory compliance. So basically, even if that's like discussed on public blockchain, it can be like a fully valid use case, I would say, in a consortium setup. So the idea is for Mixer, again, what we do basically, we just try to hide somehow the originator of funds. So we have like a couple of people like EBC, they just want to somehow hide a little bit the source of the fund. So what they do, they just send like Ether or kind of a token here into basically into a shielded pool. And then after that, these funds basically are somehow mixed together, and then after a certain time frame, they just get this fund somehow back. But basically, they are mixed in a way that the source of this fund cannot really be followed on the blockchain. So that's like the idea of a mixer. Again, practically hiding source and destinations of funds, creating a pool of funds for several people's accounts. The idea is that this can be like centralized as well, but usually if such a mixer is centralized, that there might be like certain counterparty risk or trust issues. So basically, you should basically trust somehow on this mixer, on this organization running this mixer, which might not be the best idea. So it's a better way to build something which is a decentralized mixer. It's called an on-chain mixer as well. And well, of course, it's not necessarily a very easy thing to create like a fully decentralized or a fully on-chain mixer in a way that it really it really preserves privacy as well. And there's like, again, probably infamous, but from a technical point of view, it's not it's a pretty novel idea which was used by Tornado Cash. And they realized like a fully on-chain mixer in a way that they used practically zero-knowledge proof to create basically this mixing function. And they did it in a way that basically there was like kind of an ownership proof for each fund. So ownership proof was like, I just create a password, for instance, and I just hash this password with the help of a random number, and this hash is written to the mixer as well. And basically, if I know the password of my fund, then I can get like a fund back, basically. That's like the idea. So that was kind of ownership, and the proof of that ownership was realized by a zero-knowledge proof, basically. And if I knew like a secret, the secret password, for instance, or if I knew practically the ownership, then I could get back a fund which was not exactly the origin, which was not exactly my original, but somebody else's fund. And then in this way, basically, the origin of the fund was mixed, basically. And even if everything was fully online, everything was relied in a fully transparent way, it gave like a pretty good privacy, I would say. Again, I'm not gonna discuss like the like tornado cache. I wouldn't say it's like generally a good idea. I would say that you can use something similar in a fully consortium setup. It's just because these organizations are, you know, fully legally compliant organizations, so there's not gonna be the same problems or same discussion as with like tornado cache in a public blockchain. So again, that was like Mixer. That's like the privacy use case. It's again hiding origins of funds. So let's have the second one. It's like, again, a special application as well for zero-knowledge proofs. It's basically an application as well. It's a zkML. It's a zero-knowledge machine learning pattern, I would say. And the idea is the following. So let me just imagine, I mean, AI is getting more and more traction, and machine learning is getting more and more traction. And then practically everybody just you know tries to use AI and machine learning and stuff like that overall. I mean, in all possible situation, independently if it makes sense or not. But anyway, there are a couple of use cases or many use cases where it really makes sense using like machine learning. And the problem is, if we want to use like machine learning on chain, the problem is that these machine learning models or AI models might be like big. It might takes like, you know, I mean, it like we might need like pretty heavy computation just to calculate in a way our machine learning model. Independently, if we train it might take a lot of efforts or a lot of resources. But even if we just make the inference part of that model, it's usually not something which can be realized on chain. If you think of like, you know, I mean, doing a calculation on chain is pretty limited. It's very limited if you think of like, you know, like Ethereum style ledgers. But even with Hyperledger Fabric, so usually the idea is that like, you know, do not put heavy calculation on chain to a chain code, because you might, I mean, you simply get like a timeout like after 2 minutes or for instance, and then I mean, chain code just doesn't handle very well like heavy computation. So the idea is by zkML, by zero-knowledge machine learning, is that you do the calculation off chain somewhere outside the blockchain, and then you just integrate the result to the blockchain on chain. But the point is that you should do in a way that the result of your calculation is trusted somehow. And of course, if there's like one party executing the training of your model, or basically the inference part of the model, then it might be the question how it can be like, you know, trustless. So how it can be like realized in a way that the result can be verified by like independent companies, for instance, or independent validators. And the idea is that like having machine learning and adding like something which is a zero-knowledge proof to this machine learning, and then importing the result of this machine learning with adding practically the zero-knowledge proof as well. So basically, then everything can be evaluated on chain. I mean, the result and the zero-knowledge proof can be evaluated on chain, and it's more trustless, basically. More almost decentralized, basically similarly as we have practically executed everything on chain. There are many setups of zero-knowledge machine learning and examples as well. So I will just give one example. Let me just imagine that you want to do like a credit rating of a customer. It can be realized in a, I mean, fully consortium setup as well. And then basically you just want to create the credit rating off chain, either due to performance problems. So just it might happen that the credit rating is like, you know, it is a big model, so to train or just simply to inference with that model just needs resources. You just don't want to bring it on chain. But it might happen that you just want to do somehow do this credit rating in a semi-private way. So you want to somehow bring the credit rating result on chain, but like you don't want to bring on chain some of the customer information as well. And in both situations, like credit rating, like the machine learning model for credit rating is executed off chain. by one party, and the result will be brought to the ledger. But basically, with the help of an additional zero-knowledge proof, that proves in a way that this result is correct, basically. Okay, and there are many setups here. So we can say like that the training is not necessarily proved on-chain, but it is proved basically that the same model is used for credit rating, and then just hiding, for instance, some of the information like the customer information. Okay, so that's like one pattern. I just call it zero-knowledge machine learning. The next pattern is something which is an off-chain transaction. And what we want to do here, we just want to somehow execute the transaction, but not on Hyperledger Fabric, but basically somehow off-chain, off-ledger, without Hyperledger Fabric, but in a way that basically somehow the result has the same security, privacy, or security and decentralized guarantees as we just executed on-chain. And this is like a starting point for doing something which is rollup. It's gonna be my next slide probably. But anyway, the first question is why do we need to like execute transactions off chain? Well, it is usually, the reason is not necessarily privacy. It is usually scalability. So even with Fabric, like we have like a limited number of transactions that we can execute like per minutes or per hours, and then it's, of course, every on-chain transaction is written to the ledger, so it might cause some problems with storage as well. So it might be, the idea is that we just somehow want to execute many transactions, like a couple of 10,000s of transactions per second, in a way that they are not necessary, not every transaction is written into the ledger, for instance. So if you have like such a use case, then we can think of like executing transactions off chain, but despite like written something into the ledger. So the idea is here, again, this is like a dedicated use case. It's not for general computation. It's rather for transacting tokens, for instance. So we usually think of like, we get like accounts like for Alice, Bob, Eve, and Mallory, and they just have a few tokens, for instance, and they just want to transfer these tokens among themselves, for instance. So if we have it, what we can do is that we do not store these token balances on chain, on the blockchain, and we're not going to store the transactions on the blockchains. Instead, what we do, we just create like a storage off-chain, storing the amount of tokens for Alice, Bob, Eve, and Mallory, and we just create basically a Merkle tree on that, and we just write a Merkle tree root into the ledger, into the blockchain. So that's the idea. And what we do, similarly as in a blockchain transaction, we can have like a transaction. So for instance, if Alice wants to transfer to Bob like a certain amount of token, then we can have like similar transactions, but these transactions are not written to the ledger. Instead, what we do is that we just give basically a zero-knowledge proof that, so basically what the transaction does, it's like, let's just imagine Alice has like 100 coins and Bob has like 0 coins. So a transaction might transfer 50 coins from Alice to Bob. That's like a transaction. So if you have the transaction, then basically Alice gonna have like 50 coins and Bob gonna have like 50 coins as well. So instead of writing everything to the ledger, what we do, we just create basically a Merkle tree, and we just write into Merkle tree, this Merkle tree root into the ledger in a way that Alice has like 100 coins and Bob has like 0 coins. And basically with the transaction, we can create like a new balance structure. So in the new balance structure, Alice is gonna have like 50 coins and Bob has like 50 coins as well. And what we do is that we just push this new Merkle root to the blockchain, with the help of a zero knowledge proof that basically this was like a correct transaction, and this transaction was signed by Alice, and basically it just transferred this old structure of balances to a new structure of balances, like having Alice and Bob 50/50 tokens, and then that just created a numerical root. And again, what we just write into the ledger is the numerical root and practically a zero-knowledge proof that this transaction was executed in a correct way. And that's like an off-chain transaction. So in this way, theoretically, we can just execute much more transactions than on-chain. Again, Fabric is pretty fast. So basically, usually this is not the general idea that is considered for the first round, because you might as well execute like a couple of hundred of transactions per second as well with Fabric, depending on your infrastructure. So it's not like Ethereum, where scaling is a pretty huge problem. But I mean, I would say if you want just to execute like a couple of 10,000s of transactions per second, then I mean, it might not be possible on chain, not even by Fabric. So you might consider something which is like an off-chain transaction setup. And based on an off-chain transaction setup, basically you can create something which is like a full-scale rollup. Rollup works in a way that basically transactions are executed in a way that I shown practically in the last slide. So basically, accounts and balances are basically administrated off-chain by a coordinator, for instance, and only the Merkle roots is written to the ledger, and transactions are executed off-chain as well, and basically new Merkle roots or new accounts and balances are created, and the new Merkle root is written to the ledger, basically with the correctness proof of the transactions as well. And then, I mean, that's all basically. So you can imagine it works similarly as a blockchain. We get like, old state transactions, new state, again, transactions, and the newest state somewhere at the end. But everything is running practically off-chain. So you just write in Merkle roots to the ledger, and you just give like zero-knowledge proofs to validate basically, and that shows basically that these transactions, I would say these off-chain blocks were executed in a correct way. And if you just want to create like a full-scale rollup, we can create like we have two more steps. One step is like having an off-chain token, and then we just need to transfer this off-chain token practically outside of the blockchain. That's like depositing to this rollup. It's like a special transaction, and we have like one step at the end as well, which is withdraw. Withdraw means like we have this account balance structure off chain. It is like stored by a coordinator, and then we just want to push back this token to the ledger, to blockchain as well. That's like a rollup, or that's like a general idea for a rollup. Perhaps it's again important to note that this is like one specific use case, and once this specific use case is like we have tokens and we just want to transfer somehow these tokens. So if you have some arbitrary business logic, it might not be the best idea to have like a rollup system. So another special example is again, it's still not general purpose, but that might be an interesting idea as well. If we want to do an exchange. So usually the idea to have an exchange is that we get tokens, we have like different tokens, and we just want to exchange one token to another one, or trade one token to another one. And of course, it is an interesting point in crypto, but even if you have like an organizational setup, like suppose that's like a fully regulated, business entities like banks issuing like deposit tokens, for instance, or even like, central banks issuing CBDCs, and they just want to trade somehow with these deposit tokens, for instance. So even if that's not crypto, but like fully regulated tokens, it is usually a problem to create something which is an exchange. And the reason is for that because you can do basically an exchange in a centralized way. Again, that we have just these are three banks, and then bank A, B, and C, and they issue that just deposit tokens, and they just want to exchange one deposit token to another one, for instance. So what they could do, they can just have like a new organization, which is the exchange organization, and create an exchange in a fully centralized way. But that's usually something which is counterparty risk, and then there might be trust issues as well. And so we have blockchain anyway, so let me just try to think of in a little bit more decentralized way. So basically having like a centralized exchange, even in a fully trusted setup, might not be the best idea. So instead what we can have, we can try to build up something which is like an on-chain exchange. And the problem is with on-chain exchange. So usually in exchange we have something which is an order book matching. And the problem is that the order book matching is needs data and computation. And if you build something up which needs like data and computation, blockchains usually have scalability problems. Even in Fabric, if you just want to build up basically a fully functioning order book matching, yeah, it might not work, or it might have some limitations as well. So the idea is that we can have something which is an exchange, but not like an on-chain exchange, not like an order book matching based exchange. But there are some innovative ideas as well, like liquidity pool based exchanges. It's like the most famous is Uniswap on public blockchains, and they are of course very innovative. And then they do not really have this order book matching, but they work with like liquidity pools. So they don't suffer from these scalability problems of the limitations of smart contracts and the limitation of smart contracts. But even liquidity pool based exchanges have some problems. So like they are not necessarily capital and efficient. They usually have like a high slippage. There's like additional structures, which is like impermanent loss and so on and so forth. So the idea is that we might as well build up something which is an order book based exchange, an order book matching based exchange, in a way that it is executed off chain, so not on the blockchain. So it does not suffer from scalability problems, but despite it is as much trustless or as much decentralized in a way as possible. And the idea is using, of course, SNARKs or ZK-SNARKs. So what we can do is basically we can have like, similarly as in a rollup, or you can think of like extended the rollup with like exchange functionality. So even if your amounts, if your transactions are off-chain anyway, what you can do is that you can create like an order book matching off-chain as well. And for the result of your order book matching, you can, of course, give like a zero-knowledge proof, practically a proof. So this is like an idea. It's like an innovative idea. There's like one example. It's not for Fabric, but it's like a couple of general blog posts describing how you can build up like a ZK, like an order book matching algorithm off-chain with the help of zero-knowledge proof. So basically, you have like orders. So these are the buy and sell orders. Everything is represented as Merkle trees, of course. So basically nothing on the ledger except for some Merkle tree roots. Of course, matching is similar in a sense than like transfer, but it's just not transfer, but something which is an order book matching. But the result of an order book matching is, of course, is like a new state, and the new state is represented off chain with the help of a Merkle tree, for instance. And of course, there's some cryptographic proof, zero-knowledge proof for the correctness of the order book matching. There's some proof for the correctness of new balances and the new state of the order book, and of course, correctness of the newly created Merkle trees roots before they are just written to the ledger. So again, it's like one example for possible applications for zero-knowledge proofs for Fabric. And last but not least, I would say there's like one general idea as well. It's not like a specific application. It's something which is, I would say, I mean, generally, if you want to create like off-chain computation for some reason, then you can use just SNARKs, ZK-SNARKs for this off-chain computation. Usually, the idea is that you have basically a computation, perhaps with private inputs or even without private inputs, which is calculated off-chain. Off-chain might mean here, I mean, even in the browser, but in a consortium, in a Fabric setup, this means usually like a specific organization or outside specific organizational framework. You just run somehow this calculation, you just have the result, and you just send this result to the blockchain. And basically, what you have in your chain code, you have basically this framework with which you can just validate the result of your zero knowledge proof. So basically, such a model looks that way, that basically your business logic runs outside your chain code. So your smart contract logic is realized by like a SNARK computational model. You have something which is a setup. It's like if there's like a pre-processing system, then you can just pre-process your computation and write in like your verification key and stuff like that to the blockchain as a setup. And basically what you do is that your business logic is executed off-chain, and then there's like some result and a proof on that result, which is sent to the blockchain. It can be verified basically by your chain code, and basically if it has like public data as well, it can be written to the ledger in a classical way, as usual in Hyperledger Fabric. So this is like a general computational model. I mean, in Ethereum, there's like a very big research having this generalized off-chain computation, and this is usually called a ZK-EVM, zero-G Ethereum virtual machine. Practically, it means that running arbitrary computation with the help of even like Solidity code, but fully off-chain, and despite the result is integrated with the blockchain. But I mean, it's not so easy for Hyperledger Fabric because there's no like officially there's no like possibility for Solidity development, and there's not even an Ethereum virtual machine, so it's just more tricky to do it in a totally general way. But I mean, for a certain application, it can be easily realized just having some off-chain computation and verifying the result and the zero-knowledge proofs on-chain. So, and last, there are many more applications or many more possibilities. Up to this point, I just try to cover ideas that could be like built on the top of Hyperledger Fabric. So generally, there can be like ideas of like that do not really need like application development on the top of blockchain, but you need to like fork or further develop the core platform itself. And then one interesting idea might be like the anonymous organizational endorsement. So it's like a similar pattern than the private signer. The point is that sometimes it's just a good idea to hide basically activities of a certain organization in a verifiable way. And then it's, as far as I know, it's not really possible with Fabric at the moment. So if like a certain organization is transacting on the ledger, then it can be at least seen that organization is doing something on the ledger. It's just because the endorsement signatures are in the ledger, and sometimes it is just not the best idea. I mean, especially if you have like a consortium set up for different companies that might be like competitors to each other. So an idea might be like having anonymous organizational endorsement with like predefined organizational policies, but again in a way that basically that endorsement is not really visible on the ledger. And then there might be other ideas as well, like using generally verifiable credentials with like presentations with Hyperledger Fabric for like authentication and authorization use cases. There might be some further like classical zero-knowledge applications. So I mean, especially if you have like a general application like an exchange or like a company that somehow handles funds or stores funds, then an innovative way is to like create a proof, zero proof on reserve, or it's called the proof of reserve. So practically it means that I prove for the general public that I have enough funds, I have enough reserves, so everybody can be like sure that I really have like enough funds. But I do it with a zero-knowledge proof, so practically I will not reveal how much money I have, basically. But everybody can be sure that I have a certain or more than a certain limit. It's like similar ideas like proof of solvency. It's more like for like exchanges, for instance. And then there are innovative use cases as well, for instance, like for zero-knowledge taxations. There might be some ideas as well that are more like Fabric specific and less like generally application development oriented. So like if you think of like we can have like several blockchains here, and in the situation can be like more complex, because even in one channel in one blockchain there can be like something which is a little bit like more off chain. It's called the private data collection. So we can like create smaller islands as well in this blockchain. So I mean, of course, the question is, if you have like more blockchains, more channels, and even more private data collections, then the question is if we can like connect somehow one channel with another one with some computation and with some proof for our computation, then there might be the idea just to have like zero-knowledge proofs. Of course, it can be more tricky because if you want to create the proof on chain as well, it might have some scalability problems and some performance issues as well. But if it's fast, then it might be done. So it might be done, or some clever tricks. There might be a way that we just prove something on one blockchain and we just verify basically the result on another blockchain on another channel. And then that can be like an exciting, extended cross-channel communication way of or design pattern. So actually, that was my presentation. It was taking a little bit longer than I expected, as usual. So basically, as I would say, this zero-knowledge proof generally is well, it's a very interesting topic. And then, well, I will say I'm a professional, or absolutely a professional on this topic. I would like to set up basically a learning group for the ZK and SNARK application development with Linux Foundation Decentralized Trust. So basically the idea would be that we would just cover a couple of like topics of zero-knowledge proof in a systematic way as a learning group, practically once a month during this year. And then we just get like more insights. So that would be the idea. So with that, I would like just a little bit like officially announce. I just created this funny name, which is Hunting for the SNARK. Again, that's the idea. That's a learning group for zero knowledge and SNARK, or even for STARK and other systems as well. Rather from an application development perspective. And then we would just have like one meetup each month. It's gonna be the third Thursday of each month, practically from, I guess that's 9 a.m. Pacific or 18 Central European time. And what we cover, we just cover like, I guess we start with some theoretical basics as well. It's like interactive oracle proofs, KZG, for instance, or commitments and stuff like that. But we're just gonna have like perhaps 2 sessions with a little bit like more theoretical insights. We will just continue with some specific zero-knowledge programming frameworks with like SNARK or Noir. And at the end, we would just write a couple of applications for Hyperledger Fabric. So basically, that's the That's the idea for the learning group for this year. Again, it's like the idea is like programming cool applications at the end, using Fabric at the end as a major blockchain integration, and basically that's the idea. So if you feel like learning a little bit together, then you just join this this learning group. Anyway, I have a SNARK here. It's like hunting for a SNARK is like from Lewis Carroll, and then if you just see this SNARK is basically from Half-Life, if I'm not mistaken. But anyway, so it's not like a very serious thing. It's like it's more like a fun learning group that we plan. And I would just share some more information. So basically, we just created the first event. So if you are like interested participating on this learning group, you're more than welcome to join. So the first session is gonna be on February, on the 20th of February, and then probably we just cover some theoretical basics. And again, the plan is that we will have the same 1-hour session each month, each Thursday of the month, and then we just created basically a Discord channel for coordination. So if you are interested, then basically you can find the Discord channel under community, and there's like a zero knowledge learning group. So the name is not so tricky, but basically this is like, hunting for the SNARK, funny name basically. And we plan basically to create a repo under Linux Foundation Decentralized Trust Labs. So it's gonna be like a lab with all the learning materials that we cover during the year. And then I would, David gonna approve this, but I would say anybody like having the energy joining us till the end of the years, then probably like Linux Foundation Decentralized Trust can give like a couple of merges at the end. Again, it's probably for those who manages like writing a couple of few example applications as well or something. So that's the idea, and that was my presentation. So I would like to thank you very much for your attention, and then we can likely have like questions and answers at the end. I'm happy to answer any questions that I can.
Hi, Daniel.
Hi.
That was really informative. Thank you so much. I think, like I just come across this meetup, and it was really on my plan this year to get involved more on learning blockchain. So can you please just share the link of the Discord in the chat, if you may?
Yep.
So
absolutely.
we'll be able to probably try to get engaged more and more. Do you have any like a source for like beginners to start learning? Probably blockchain website itself, huh?
Yeah, absolutely. So basically the idea is that as we just follow with this learning group, I will share everything in this Discord channel that I can. And again, there will be like it's like a Linux Foundation lab, decentralized trust lab. It's again, it still doesn't exist. It's still in the pipeline. But like in 2 months, we will set up a lab, and I will share every piece of information that I have basically there as well. But again, for the first one, I would say Discord is the first step, and it's, as you see, it's still empty. So we just created basically yesterday. So it's just my welcome message. Again, everybody is welcome to join. But I will share as much information as I can here, basically. So I would say I don't have at the moment like a full list of, I mean, existing existing links, but we will have till the end of the year. That's the plan.
Great, thank you. I'm excited.
Yeah. So that's a good question. If there's community or people working on verifying the implementation of ZK proofs for Hyperledger, that's a good question. Not that I know. I know a few companies who specialize on verifying zero knowledge computations or zero knowledge proof, zero knowledge based applications. But basically the main direction with zero knowledge proof is like Ethereum and public blockchain. So Fabric is not so much hyped. I would say so there's less traction. But I mean, I will take a look. I think companies having like services for verifying general zero knowledge computation, they can offer service for practically any kind of blockchain. So they can be like contacted if they manage like, or if they just yeah, manage to do like verifying like zero knowledge or validating or auditing zero knowledge proofs for Fabric as well. I will just Google a little bit and I will share a couple of examples. Again, these are companies generally auditing zero knowledge proofs, not necessarily for Hyperledger, but I mean, perhaps they manage for Hyperledger Fabric as well.
Hello, Daniel. Thank you for the session. I am a beginner on this blockchain and related technologies. I am just starting with these things. I have basic idea about this. What are the opportunities that this learning group would provide for me?
Yeah, that's a good question. So basically, what we try to achieve here is that we just try to summarize some knowledge, some know-how generally for zero knowledge programming. Again, more like from a developer and application programmer or application developer perspective, and not necessarily from a deep cryptographic point of view. And we just try to build our applications at the end for Hyperledger Fabric. Again, that's like the target blockchain. So if you're interested in having some more in-depth knowledge for the ZK technology, for ZK programming, and eventually like building up complex applications based on ZK, then I would say then this learning group can offer you a lot. Yeah, so that's the idea.
Thank you. Thank you.
So any more questions?
What are there any basic requirements to get involved in this group? Because I know some of the graduates who are getting out of the college. I'm thinking of involving them as well. They are my juniors, but they are just getting out of the college. So is it a good idea to involve them in this?
Yeah. So generally, probably I'm gonna have so based on this again. So this is like a 1 year learning group. But probably based on this learning group, and especially if you just collect the materials. So what I do, I teach at 2 universities, and then probably I will have like a course based on the experience of this learning group. That's gonna be probably somewhere Q3 and 4 this year, or probably next year, and it's gonna be like for software developers, software engineers, and applied mathematicians. And it's gonna be like a full-scale course. So based on the experience of this month, so I would say, yeah, it will be on a long run a basis of a university course as well. I'm not quite sure if that fully answers your questions, but basically that's the idea.
Yeah, understood. Thank you.
Anyway, we're gonna share the slides and the links as well after the meetup. So yeah, you're gonna see these links practically in a mail as well. So just don't worry about if you just didn't catch it. So any more questions? I mean, if there's no more questions, I would say I would like to thank you very much for the attention. And then, yeah, if you're interested in participating in this again exciting learning group, again it's just 1 hour each month, third Thursday, and then we will just cover zero knowledge SNARK programming and some application developments based on these topics throughout this year. So yeah, just feel free to join. And again, thanks for your attention. And then, well, if you join, then happy hunting for the SNARK.
Yeah, sure.
Thank you. Thank you.
Brilliant. Have a nice evening. Thanks.